In this sequence of videos, we're going to discuss the graphs of exponential functions. Let's start with the exponential function f of x equals b to the x. This will give us a graph that will look slightly different depending on what b is. When b is larger than 1, we have what's called exponential growth. And when b is between 0 and 1, we have exponential decay. Remember, b is not permitted to be less than 1. It's not permitted to be less than or equal to 0, and it's not permitted to be equal to 1. So we can sketch what the graph looks like relatively quickly. Let's go ahead and draw some axes here. And we'll fill in just a couple points, and we'll make a couple observations, and we'll make a couple recollections from previous material. So first of all, the graph of b to the x will go through the point 0, 1. That's because b to the 0 is equal to 1 for all b. It doesn't matter what b is. Anything to the 0 power is 1. Now b to the first power, that's just going to be b. And so if x is 1, then the y value will be b. And depending on what b is, if b is bigger than 1, that will be something larger than 1. And if b is between 0 and 1, that will be something smaller than 1. In the case of b larger than 1, the graph is going to look something like this. And this is just the general shape of the graph. This is what I would say qualitatively what the graph looks like. That is, I'm not taking a bunch of x's and putting them into the function, evaluating them, and plotting them precisely. I'm simply sketching what the curve looks like qualitatively. And then for my exponential decay example, for b being between 0 and 1, the graph is going to look something like this. So both of these are sketches of b to the x. In this first sketch that we did, b is bigger than 1. And in the second sketch that we did, this is b to the x, where b is between 0 and 1. Of course, there are similarities and differences between these two graphs. Let's go through some of them. Some of these will be review from previous. So both are 1 to 1. So b to the x is 1 to 1. It passes the horizontal line test. So that's how we know it's 1 to 1. This graph of b to the x has a horizontal asymptote. At y equals 0. Now, for exponential decay, you get close to that horizontal asymptote as x gets really, really large, and for exponential growth, you get close to that asymptote as x gets very, very negative. But both of them, both of the graphs have a horizontal asymptote at y equals 0. The domain of both of these graphs is all real numbers. Another way to phrase that is you can take any x value and put it into the function b to the x and get a meaningful output. The range of both of these graphs is 0, infinity. So the y values bigger than 0 are attained. You can tell that by drawing a horizontal line at any y value larger than 0, and you can see you get an intersection with the graph. Whereas if you draw a horizontal line for a y value less than 0, there is no intersection. If we take a look at the graph of these, let's clear some of these marks up. We see that there is no intersection with the x-axis, and there is one intersection with the y-axis at the y value of 1. And so we would say that there are no x-intercepts because there's no intersections with either graph with the x-axis. And the y-intercept is at 0, 1. Finally, for b greater than 1, in the case of exponential growth, the graph is increasing all the time. So the graph is always increasing. And frequently I'll just draw an up arrow to indicate increasing, and if b is between 0 and 1, so the case that we have with exponential decay, the graph is decreasing. Now, if you come across an exponential that you'd like to graph, it's relatively straightforward. Let's say we wanted to graph f of x equals 1/4 to the x. And let's even make it a little bit more complicated. Let's say it's 3/4 to the x. What you can do is you can take a few x values, make a table, and connect those points that result from the table that you just created. So my advice is, for a simple exponential, you could pick x values of -1, 0, and 1. So in this case, we have x and we have 3/4 to the x, -1, 0, and 1. When x is 0, you're always going to get 1 no matter what b is, because anything to the 0 power is 1. This will end up being 4/3, because if you do 3/4 to the -1, that is 3 to the -1 over 4 to the -1, which is 4 to the first over 3 to the first, using properties of exponentials. And 3/4 to the first power is just going to be 3/4. And so you can go ahead and sketch coordinate axis here. Now keep in mind that we have our function is 3/4 to the x, so b is equal to 3/4. Since b is between 0 and 1, we should get a graph that looks like exponential decay. If you don't, then you know something went wrong. So at -1, we have 4/3. That's a little bit bigger than 1. At 0, we have 1, and at 1, we have 3/4. And if you needed to evaluate more, you could, but this graph is going to look something like this. And what I mean by that, if you need to evaluate more x values, if you want more points to connect because you don't exactly know how you should connect these 3 points, you can always include more x values in your table. And those are some of the very basic ideas of the simplest type of exponential function that we can find, b to the x power.